Okay, so this is going to be the YouTube video for the 3 extra credit assignments for Mr. Wellman's physics class. I have put them all into one PowerPoint and therefore one video just to make it easier for me and probably hopefully make it easier to grade. So here we go. The first one is the yes-no device. So here is a diagram of the setup. So I'm using the piece of wood that you gave me, and then I have these blocks of woods written no, like N for no, Y for yes on them, and they're at different lengths. So I'll explain like the rationale for the different lengths later. So the explanation of the physics, small oscillations of the wood that match the frequency of each block will cause them to move. Since their lengths are different, they have different natural frequencies. So each block can be moved individually as a result, meaning that you can make subtle movements with the block and it will cause, or subtle movements with like the base stick, and depending on the frequency or the period of that, it'll cause one of the two blocks to move if the frequencies match in that scenario. So this is the work shown. So I'm using the equation t period equals 2 pi times the square root of L over G. I'm using 9.8 meters per second squared for gravity. And so you can see for the yes block here, the length of the string I measured to be 43 centimeters or 0.43 meters. Plugging my work into here, eventually solving for F. I have that the frequency is 0.75 cycles per second, or that the period is 1.3 seconds, meaning that if I move the device one oscillation in 1.31 seconds, it'll cause the yes block to move. Next, we have the no block. This had a shorter length of 34 centimeters or 0.34 meters, and I found the period, which I didn't box, but the period is right here, to be 1.17 seconds. So if I move the base stick with a slightly quicker period, it'll cause the no block to move. Different gravities. So to answer this question, this device would not perform differently on a different planet. This is due to alternate gravities. So higher gravity would decrease the period and increase the frequency. You can see that with the equation here. So the higher gravity here in the denominator would cause, if you have a larger number in the denominator, it'll decrease this t period, which would cause an increase in the frequency. And vice versa if you lower the gravity. Here, I hope this works. Here's a video of the device, of me asking the device a couple questions.
Sample questions for the yes-no machine. Is the month right now May?
That was a yes.
Did the Seahawks win the Super Bowl this year?
Pretty obvious no.
Is the sky blue on a clear day?
Supposed to be a yes.
Is school out in mid-June?
It's a yes again.
Is my name Frank?
Okay. So you see the device works marginally well. The next extra credit assignment was measuring the mass of an unknown object, well, of a known object with unknown mass with just a rubber band. So here are the 3 objects that I wanted to measure the mass of. These pliers here, this water bottle, and this block of wood. The device I have here, I have this rubber band that was given to me, and then just for ease of tying it to things, I added this little, this little rubber circle to it. The explanation of the physics, so qualitatively, the rubber band has a constant K value. The rubber band is a spring, so you can think of it, so you can use the spring formula in this scenario. With the same spring, so if you have the same spring, you'll have the same K constant. Increasing the mass will decrease the frequency, and decreasing the mass will increase the frequency. This will become evident when we look at the equation in a second. And from this, if you know K and you know frequency, mass can be determined. So here's my work for that. First, K was determined with a known mass. So I have mass of 300 grams, and I measured the frequency using a video so I took about a 10-second video, and then I saw that 10 cycles occurred in that time, so that goes down to 1 cycle per second. Putting those values in, I eventually find that K equals 11.84 kilograms per second squared, which no, I'm right because that's the correct units for K. Then for the subsequent calculations, I rearranged the frequency equation for mass because that's what we're solving for. And yeah, so eventually mass equals the K constant divided by 39.4 times the frequency value squared. So here's my work for each of them. So for the water bottle, through a video, I found that it went through 1.33 cycles per second, plugging those values in, the K constant here with the frequency. I eventually have 0.169 kilograms as the mass of the water bottle, or 169 grams. For the wood block, similar situation. I found that the frequency to be slightly less, so 1.09 cycles per second. Meaning, so I intuitively know that this frequency is less, is going to be a heavier mass, and the math shows this. So plugging in the values, I found that this final mass for the wood block is 253 grams. And then for the pliers, pretty simple. We have 1.11 cycles per second, which is similar to the wood block. And so we would assume that they are going to have similar masses, and they do once we work out the math. So the pliers weigh 243 grams. Lower and upper limit. So the upper limit is a mass so great that it would stretch the spring enough to change the K constant. So we would say that the rubber band or any sort of spring is elastic, and for something to be elastic or plastic, it can go back to its original shape and it would maintain its K constant. But if you took it too far, you would stretch it out and actually change the structure of it, and so the K constant could change. This would change your values, or if you broke it, obviously it wouldn't work either. Also, changing the length of it would alter it too. That's not what's being asked here. The lower limit is that the mass must be great enough for oscillations to even occur for you to observe the oscillations. According to the equation, you can see that if the mass were to approach 0, the frequency would approach infinity, and you can't really measure infinity. And so you need to have something that's at least partially massive for this to practically work. Mars versus Earth. So this is another gravity question. The gravity on Mars is less than on Earth. This means that there is less gravitational force on each object. Therefore, an object on Mars would oscillate faster than on Earth, and lower gravity would increase period and decrease frequency. So the final extra credit here, moving on, is finding the radius of a circle. And so in class, this was done using a mirror. And it's not a full semicircle, but really this kind of cut of the circle. And I measured that the length of the circle here, or length of the section that I have, to be 40 centimeters, then the height of this dish, essentially, this parabolic mirror, to be 3.4 centimeters. Using my Pythagorean theorem, I inferred what the radius is by creating a right triangle here. So for the base of my right triangle is x over 2, that squared, plus the height of my right triangle, which is r minus h squared, would give me my radius, because taking a line from here up into the center with this relationship here between r minus h would give me my radius. And so I'm plugging these values into just regular Pythagoras. I'm rearranging, expanding this r minus 2 squared. It's nice that moving this r squared over, the r squareds cancel, so eventually we have 0 equals 138.4 minus 4r plus 4. Oh, sorry, I don't have units on these. So these are all centimeters. And eventually we solve that the r equals 35.4 centimeters. Based on this Pythagorean equation. So that's all I have. Hope you enjoyed. If you have any questions, please let me know. Thank you.